Dr. Mamedov, please. From Institute for Physical Problems, Baku State University. One of our leading scientists. Okay.
Okay. Thank you giving possibility of giving the talk. Actually, we prepared this talk for posters, so just okay. Today, okay, so I will here present some small our results because until this conference we participated in several conferences and gave extended talks there. So we work in the field of holographic QCD. So there is two approaches in holographic QCD, as you know, top-down and bottom-up approach. We usually deal with bottom-up approach. There are two models in bottom-up approach, two main models. There is several models, soft wall and hard wall models. This is holographic QCD. There is five in the bulk of five-dimensional ADS space. Oh, next slide. Okay, there are left and right gauge fields in the bulk of ADS five-dimensional ADS space, and besides complex scalar phi, and so action for this fields are usual, are defined in the usual way, and axial vector fields field is defined by means of left and right gauge fields, and if right explicitly gauge action for gauge field and phi field we need for in order to break chiral symmetry SU2 left across SU right. So this is action for the phi field, which includes p pions. Further, we shall correspond to these pions on the boundary of ADS space. So next slide. Okay. So we compose in such a way complex components of vector field, axial vector field, and interior components. Okay, next slide. Okay. So equation of motion for the A1 field, axial vector field, it has such a form. Explicitly, if write in Poincare coordinates, ADS space, this equation is this explicit form, and in momentum space, we apply calculate the composition. Firstly, we can consider, in order to solve this solution, we can consider ignoring this condensate term usually, in which usually use ignoring this condensate term and solve this equation, and solution is usual Bessel function. And we wanted to somehow to include this condensate term in the solution also. So as you know, we deal with a Hardwell model. So in Hardwell model we have two limits, infrared and ultraviolet boundaries. So we have decided to solve this equation at infrared and at ultraviolet limits. So in such a way to find approximate solutions. Somehow, next slide. Okay, we take values, these values of these terms. We see that one divided by ZIR squared is more than this term. Previous, please. Okay. So in the equation we see that this term, in fact, even at the IR limit, less than this term. So in this limit, so we can solve. Okay. So solution is again Bessel function. Kind of solution. So, but here mass include condensate term also, and we can write it approximately. So finally, profile function for axial vector field, which includes condensate term also, as such a simple form as usual one. The solution distinct from earlier ones by just only that the mass coefficient it contains this condensate in such a form of approximation. We take into account condensate term also. Okay. Thank you for attention.
Okay, thank you, Professor Mamedov. Okay, any questions from online connection or from audience? Any question, please? If there is no question, and let's applaud Professor Mamedov for his interesting talk. Thank you very much. Break, and after 15 minutes, and there will be connection, and the next session will start.
Mr. Tabahira, we connected after 15 minutes. We have a break, coffee break. After 15 minutes, we connect, and we're waiting you participate in our conference. We're waiting you talking. Yes?